Hello everybody, welcome back to another concrete design video. This one's going to be on slab analysis and one-way slabs, and we're going to be looking at a very simple problem to explain how to analyze a one-way slab. And just to preface it, this is super similar to what we've talked about before with flexural concrete members. So if you need a brief summary of that, you can click the link at the top. But to hop into this problem, we should first look at some important keynotes, which are the differences between slab systems that we're going to be looking at in this program. So we have one-way slabs and two-way slabs. In this video, we're going to be looking at one-way. And the simplest definition for a one-way slab is in the name, where approximately 90% of the load in the slab or on the slab is going to be transferred in one direction only. This is a load transfer mechanism for one-way slabs where the load is transferred in the short direction. And we can classify this slab by looking at the spans in the north-south, which is Ly, and Lx, which is the east-west direction. Now, when Ly over Lx is greater than 2, we are defining our conditions and classifying our slab as a one-way when this condition is met. But how can I prove what I just mentioned earlier? I mentioned that 90% of the load is going to transfer in the short direction. Well, we can look at a typical one-way slab configuration, which I've set up here, and look at the Ly and Lx. But now I'm going to set Ly equals to 2Lx to satisfy that one-way slab requirement. Now, what else do we know about this slab? We know that max deflection will be in the middle for a uniformly loaded slab. And since these strips share the same midpoint, we can use the same equation for deflection for both, assuming that we have simply supported conditions for both ends. However, when we're looking at the load taken over the red strip, we have Wx. And when we're looking at the long blue strip, we have Wy. Now, we already talked about, we have the compatibility condition where at the center, both of these spans are going to have the same deflection. So we set them equal to each other, and then we go ahead and simplify these equations and plug in that new value of Ly equals to 2Lx and simplify everything. At the end, we're going to be left with Wx is equal to 16 Wy. This means that the short span is now taking 16 times more load than the long strip, which is the key important point to be taking away here, is that in the one-way system, that short span is going to be taking majority of the load on your slab. Now, for design purposes, we're going to be assuming design strips, and I've already kind of briefly touched on this with these red and blue strips in that problem there. And design strips are basically a way to simplify analysis and design for slabs. And that's when we take a 1 meter segment for our slab and do analysis for that 1 meter segment. And then once we have information about this segment, we can then apply this to other regions on the slab with respect to that short span, okay? And this is going to vary, obviously, if you look at a negative moment region versus a positive moment region, because the area of reinforcement will be either on the top or the bottom. But all we need to know for now is that for slab analysis, we're going to be looking at 1 meter segments or strips. This also means that when we're designing for steel, we have to consider that 1 meter segment as well to quantify an area of steel per meter in that segment. We're going to see all of these concepts applied in this problem right here. Alrighty, so now I've cleaned up the side here. Now let's hop into the problem. We have a typical cross-section for a properly reinforced one-way slab, and the slab is 200 mils thick with 15 m at 300 for the reinforcement. That's on the bottom tensile face. It's telling us that the effective depth is 170 mil, and wants us to determine the factored moment resistance for the slab strip. And it gives us all of our parameters that we need to work with. Now, first things first, I just wanted to briefly cover, once again, we usually assume alpha 1 and beta 1 as 0.8 and 0.9 respectively when we have an FC prime between 25 to 40 MPa. That's just typical. You can check the formulas if you want to, but they're generally close to these numbers. So I'm just going to assume these numbers right off the rip. Now, the next thing that we need to look at is this area of steel that we were talking about. Since we know that we have a slab segment now, we have to consider a 1 meter segment and then convert this area of steel into a per meter value. And we do that by using this formula. For a 15 bar, we have a 200 meter squared cross section, millimeter squared, sorry. You have that 1000 millimeter segment that we're considering. And that's all over the spacing of our bars, which is 300 millimeters. And then solving for this, you're left with approximately 667 millimeters squared per meter. Okay. Next thing that we need to do, obviously for the alpha value, we have to figure out a way to get to this A value. And in this formula, we have TR on top over alpha 1, phi C, FC prime B. So we can first solve for this TR value by simply writing down TR is equal to phi S AS FY. Solving for that, we have 0.85, that area that we just solved for, 667 millimeters squared per meter. That's Fy for a properly reinforced segment of 400 Newton millimeters squared. And then simplifying this, you'll be left with a value of 227 times 10 to the 3 newtons, and that's per meter once again. So every per meter segment, we have a resistance or a tensile resistance of 227 times 10 to the 3 Newton per meter, right? Let's go ahead and figure out what the A value was. We have TR on the top over all of these design variables, alpha 1 phi C, FC prime, beta, or B, sorry. And we're simply plugging in once again. We have 227 times 10 to the 3 on top. This is newtons. And then we have alpha 1, which is 0.8. We have 0.65 for phi C. FC prime 25 Newton per millimeter squared. And we have the B value, once again, as 1 meter, or 1000 millimeters, which leaves us with an A value of approximately 17 millimeters. And now we can simply go ahead and plug in for our moment resistance. Super easy problem. We have TR D minus A over 2. We know our TR, which is 227 times 10 to the 3 Newton per meter. Our D is given as 170. Then we're subtracting 17 for A. That's millimeter. And then solving for MR, we have a value after converting to 37 kilonewton per meter. So this is a resistance per meter value. So every meter segment of this slab is going to be able to resist 37 kilonewtons per meter. Right? So that's your final answer for this problem. And I hope the explanation helped to understand the difference between one-way and two-way slabs. We're going to cover a lot more problems like that in the future, but I thought it was important to cover before hopping into this problem. So hope this helped. Thanks for watching.